Okay, good evening. I've got the thing recording. So this is a kind of 2.5-part thing. One part is me mostly showing you pictures. There's a lot of words that'll be up there as well, but you don't have to worry about most of them. They're either to remind me to say something, or these are mostly slides I use in my classes here, and I just didn't get around to removing the words. So don't worry about all the words. Next door, there will be an impact simulator practice exercise where you guys can do your own experiments. And, of course, don't forget to measure things. It's only science if you write it down. Okay? So measure and write it down, but do have fun exploding cocoa powder. And then out in the hallway, we have an interesting collection of rocks, many of which came from space. So there are a bunch of meteorites outside that you can touch and look at, and little magnifying glass you can look at, make them look bigger. We also have a couple of rocks that are made up of the debris from large meteorite impacts, one from Canada. All right, because we have a much younger than usual audience, I doubt your attention span is any less than most of our undergraduates, but I'm going to try to keep it exciting. But if you have a burning question that you want to ask, please just raise your hand, and if I don't see you, then just shout. Not too noisily, but just get my attention, and I'm happy to answer questions as we go along. Also, in case you need the bathroom, it's out that way, but the students outside can help you with that. All right, so let's start. When I put this together, and actually we did this 2 years ago, so this is kind of a rerun, so I think it should go okay. I thought of what are the 4 questions that kids might want to know about meteorite impacts. So probably the first one is going to be, how often do these things occur, and should I wear a helmet on my way home tonight in case something happens? So we'll talk about that first. And in case you're worried, the main answer here is they're not very common. These things are really cool, and part of the reason that they're so cool is actually they are very, very infrequent, very rare events. If they happened all the time, we probably wouldn't think they were very cool at all. Another question, what are meteorites made of? I'll tell you a bit about it, but there's no substitute for actually going outside and picking a meteorite up afterwards and looking at it. How big would the crater be? I have a bunch of students actually working on a homework assignment to figure out how big different craters would be. You guys are going to get to make your own to find out. And then finally, how can we avoid being hit? That kind of goes back to the first one. We don't really want to be hit by a meteorite. We'll talk a little bit about that. But all of these I'm going to try to keep fairly short and moderately fun, and much bigger letters than I normally use on slides as well. Anyway. All right, so the first question then is, how often do meteorite impacts occur? How often do meteorites land on the Earth? Now, the answer to how often do meteorites land on the Earth is very, very frequently. Here is a video shot in New York in 1992. This is a fireball streaking across the sky. You can see little bits breaking off, burning up. There's lots of good videos of this particular one because it happened to go right over a high school football stadium, and it was on a Friday night. So there were lots of people with video cameras who took a brief moment away from the football action to video the fireball. Anyway, so very, very small things land on the Earth pretty much every day. Little bits of dust, maybe centimeter-sized things. I say land. Mostly they don't land. This one did. This one hit a car. It's pretty unusual. There was a mailbox being auctioned on eBay a couple of years ago that had been hit by a meteorite as well. But anyway, it's pretty unusual. But occasionally you'll get one. I remember a few years ago there was one landed in Chicago, and a few pieces went through some houses. Ones that are really dangerous, that might destroy a city, they only happen every 1,000 years or so. And the really, really big ones that affect the whole planet are extremely rare, every ballpark 100 million years. It's important to emphasize this is on average. This is not a fixed timetable. We can't make a schedule of, the next one's coming next Tuesday. This is just on average. But on average, they're pretty infrequent. So here's kind of a graph to show that. basically what it says is that the bigger the impact, and for those of you who can read it, the scale along the top is in like numbers of atomic bombs. So some of these are quite big. In fact, the atomic bombs are at the small end of the scale. So the big end of the scale over here is actually way more than if all the world's nuclear bombs were detonated simultaneously. The good news is that that end of the spectrum is also extremely rare. Again, it's that every few tens or even hundreds of millions of years that might happen. There's one that's kind of highlighted, which is Siberia, this one right here. This was a place called Tunguska in Siberia. How many of you have seen Ghostbusters? All the older ones and not so many of the young. Okay, right. Anyway, in Ghostbusters, Bill Murray, Dr. Venkman, yes, he talks about the Tunguska event. He gets the year wrong. That always bugs me. Anyway, so the Tunguska event was this fairly big thing, big explosion that was heard actually in Western Europe, so thousands of miles away. And it devastated quite a large area, but all that was there was trees, and pretty much nobody lived there. So we don't know much about it. That's kind of interesting. That was like the biggest thing that's happened to us coming from space for a long time. You may remember just a few months ago the Chelyabinsk meteorite that we have lots of videos of because everybody in Russia has a dash cam on their car apparently. That was actually not a particularly big one, although it was kind of impressive. Okay, so why have impacts been in our consciousness? Why is it something that people even think about? Mainly it comes from this thing that happened in 1994. Again, for the younger people in the audience, this is an unimaginably long time ago, but ask your parents about this. They remember the early 90s, vaguely. And there was a comet that hit Jupiter. So this comet, not only did it hit Jupiter, but it broke up into all these different pieces. So here's a photo, and they imaginatively labeled all the pieces with different letters. And so this thing broke up, and then piece after piece after piece collided with Jupiter. This was the first time that anybody had ever seen two different bodies in the solar system collide. And this is a kind of photo. This is not actually light we can see with our eyes. It's light of a different wavelength. But this is a photo of fragment G, one of those fragments of the comet hitting Jupiter. And on the other side, I can't quite reach it, but top right, you can see a slightly lighter patch there. That is still the kind of the leftovers from the impact of fragment A. If fragment G were to hit the Earth, this is kind of what the Earth would look like 100 minutes later. I don't know why these things always target New York or DC, but it happens in the movies, so I guess that's what they did here. Anyway, it would be a very important thing. It would definitely be the news headlines that day. The last time a really, really big one, something like that, happened on Earth was what we call the end of the Cretaceous period. And basically, this is when the dinosaurs disappeared. This is obviously not a photo. This is a really cool painting by this artist, Don Davis, of what that might have looked like. So there is the Earth. You can kind of see the curvature of the Earth and see how big it is. And this is the splash, basically, that this impactor produced. Another artist's impression, and here it is just landing, much to the consternation of some pterodactyls. And then, of course, it landed in Mexico, actually, the Yucatan Peninsula. So not too far away, and there's lots of stuff from that impact that we can find in the US. I love this. So we have these enormous kind of tsunamis, and because it landed in shallow sea. I don't know if you can see here, but here's a triceratops that got knocked over. And here's an elasmosaurus kind of going, what? Just as it gets, completely washed away. Anyway, so this is kind of a brief history of life on Earth, the last 540 million years. And each of these spikes is a time when lots of things went extinct. And you'll see that the end of the Cretaceous here, this is not the biggest one, but it was certainly one of the major ones. That was the end of the dinosaurs. Interestingly, the biggest one, the Permo-Triassic here, this is when the dinosaurs began. So actually the history of life on Earth is kind of reset every couple of 100 million years by major events. Which brings me to the geologic time scale, because, not enough of you are familiar with this. This is where I need a volunteer. I could probably have 2 or 3 volunteers, actually. Let's see. All right, I'll take 1, and 2, and 3. All right, so state your name and age.
8.
Connor, 8.
9.
Oh, just say you're 9. Yeah.
7.
Is he 7? And 8. Cool. Okay. So this is the geologic time scale done on kitchen rock. So every sheet is 50 million years. So we're going to see how long ago is it. They might say the dinosaurs went extinct 65 million years ago. That doesn't mean very much, unless you're familiar with thinking about millions of years. So let's look at it in the perspective of Earth history. So your job is going to be to take this end, and let's have you stand here. Right. Yep, that's good. All right. And then you guys are going to kind of take over and hold this in a minute. So 4,550 million years ago, that's 4.5 billion years ago, formation of the solar system, meteorites, the ones that are outside of the Earth. Formation of the Moon happened about 50 million years after that, and that was caused by an enormous impact. A small planet hit us, and that led to formation of the Moon. And then 1,400 million years ago, this is the oldest piece of mineral that we've ever found on Earth. A single crystal, a tiny microscopic crystal. Earth's atmosphere formed around 4,200 million years ago, but there was no oxygen. If you ever build a time machine and go back 4,000 million years ago, you must take oxygen with you. Okay? Very important. 4 billion years ago, the oldest known rocks on Earth. I actually have the piece, I didn't bring it with me tonight, but just over 4 billion years old. It's the oldest known rock. It's from the Northwest Territories in Canada. We've now left the Hadean and entered what we call the Archean. We have the oldest known sediments, so dirt basically, Isua in Greenland. And you'll notice we have lots and lots of these sheets where we really don't have anything written down. That's because there aren't a lot of rocks that are this old that we can find. I'll meet you guys in a sec. Alright, oldest known life. We have good evidence for bacteria and algae at around 3.5 billion years ago. Wow, 3 billion years. Alright, I need one of you. Alright, so you hold also right down there. Alright, stay there. Is even you go ahead of me? Okay. Alright, 2,700 million years ago, now we start to get atmospheric oxygen and we get a whole bunch of stripy rocks with iron in them. Now we're entering the Proterozoic, 2,500 million years ago. 2,000 million years ago, 1,800 into the middle Proterozoic. We have a few rocks at this age, but there's a lot that we really don't know about all this time. Oh, 1,400 million years ago, one of my favorite parts, volcanoes in southeast Missouri. At this time, how many of you have seen Alfred Rocks or Johnson Châtaignes or that part of the world? Yeah? Okay, so that used to be like Yellowstone. 1.4 billion years ago. So Johnson Châtaignes are all the product of huge volcanic eruptions. Gold Salt, the highest point in Missouri, is covered in a rhyolite, volcanic rock, formed in a huge explosion. We think there might be some animals about 1.2 billion years ago, but we don't know. We have something that's kind of like footprints, only we don't have footprints of those animals because they didn't have feet. It's more like a valley print. I guess it's quite hard to be sure that it's a valley print from not just. Supercontinent Rodinia breaking up. So I'm not going to talk about supercontinents tonight. Oh, about 700 million years ago, the Earth was completely covered in ice. All the way around, it was snowball Earth. Then that melted, but now entering the Cambrian. This is the place actually. Something about 550 million years ago, we get large living things that are not just algae, not just bacteria. And 488 early fish, 450 early land plants, 400 insects, 350 reptiles, early trees, lots of coal. We just assembled the supercontinental Pangaea about 280 million years ago. Into the Mesozoic era, the first dinosaurs, 215, the Atlantic Ocean begins to open, early birds and mammals, 150 million years ago, early flowering plants, 65 million years ago, the dinosaurs just got destroyed. And then this very last sheet from the last 50 million years, of which I've used this a few times, and actually we're mostly frayed away. The Australopithecus here at 3 million years, one of the oldest hominid fossils. That's kind of the last less than an inch. And Homo sapiens, of course, evolved in the plot right at the end of that very last sheet. So that's how big geologic time is. And the extinction that led to the end of the dinosaurs is just more than one sheet from the end. So when they say that every 100 million years or so we get one of these really big impacts, geologically it's pretty frequent. On a human time scale, you can sleep quite safely tonight. I would like a big round of applause for my helpers. Alright, and I'll need even more applause if they can manage to roll the whole thing up. Did you kill it? Don't worry. Alright, so where do we find impact craters on the Earth? All these red spots are places where meteorites hit the Earth. Now, one of the kids, pay close attention to this map and tell me where do meteorites apparently not land? Linus.
In the middle of Africa.
In the middle, that's true. There's a gap in the middle of Africa. Where else?
Mostly in the ocean, there's only like one.
Yeah, right. So now this is actually known impact craters. Why don't we have any known impact craters in the ocean? People can't go and check. To a large extent, that is correct.
And also, there can't be a crater in water.
There can't be a crater in water. That's true. You could make a big splash, but the water flows back again. There could be a crater on the seafloor, of course, but in most cases we don't have the seafloor particularly well mapped. If you're geology students, I would tell you about plate tectonics and how the oceans are no older than 200 million years, whereas the continents are much older. So that's another reason that the oceanic crust has not been around long enough, but that's a whole separate thing. So yeah, we know about craters that are exposed on land, and mostly actually you'll see that they're very concentrated either in areas that have been mapped very carefully for their geology, or places that are deserts, and when there's a crater you can really see it. Linus, do you have a question?
Why haven't you found any meteorites that hit?
Good question. Right, so what about the South Pole? Most of Antarctica, of course, is under ice, so the geology there, in a lot of places, we don't know it very well. But people go to Antarctica every year to find meteorites. Because if you're in the middle of the polar plateau, where there's only ice, and you find a rock, there's only one place it could have come from, which is the sky. So actually, it's a great place for finding meteorites. What if the Earth didn't have all these active things like plate tectonics and wind and water and erosion and everything else and plants? You know, personally, as a geologist, plants annoy me because they get in the way of looking at the rocks. At the same time, I'm grateful to have oxygen to breathe, so I can't get too mad at them. But if you go to the moon, which has had nothing really happen to it except to be hit by bits of space debris for the last 4.5 billion years, we can tell which parts of the moon are older and which are younger by how much craters they have. So the lunar highlands, these really old parts, these are nearly 4.5 billion years old. And you can see that they have been hit by so many things. The lunar mare, the seas, which are actually not seas, they're full of lava. Oh, now it's all solidified, but they're actually full of lava. They tend to be very smooth, and they're much younger. And in fact, they fill old impact craters. That's why they tend to be circular. All right, what are meteorites made of? Anybody know what meteorites are made of? Yeah.
Ice and space-time and stuff like that.
So ice, certainly we can have comets have a lot of ice. Benjamin?
Really actually little pieces of meteoroids.
That's okay. So, yep, what are meteoroids made of? So we call them meteorite if it actually lands on the Earth. It's a meteoroid if it's still flying in space. They're basically made of bits of rock, but where did the bits of rock come from? Okay, occasionally we get bits of the moon or Mars that fall to Earth as meteorites, but that's extremely unusual. And by the way, the only way that happens is if there was a big impact on the moon or Mars and it blasted chunks of that out into space and some of them hit the Earth. And that's kind of cool. Anyway, but mostly they're leftovers from the formation of the solar system. So the solar system formed from a nebula, a big cloud of dust that was spinning around, and it condensed into clumps, which formed into planets. But then there were a few bits that were left over. And some of these are found in the asteroid belt. And the asteroid belt is between Mars and Jupiter. I'm not worried too much about that. Anyway, so the asteroid belt between Mars and Jupiter. This picture, the green dots are asteroids. The red dots are asteroids. The red ones are ones that come within a certain distance of the Earth from time to time, and so they're coded red for danger. So the Sun is in the middle, then Mercury, Venus, Earth, Mars, and then this is the asteroid belt. So you can see there's quite a lot of them around, actually. And since we've really started looking, and people have been looking pretty hard for these for more than 10 years now, they've found thousands of them. Also, NASA and other countries' space agencies have started to send spaceships up to actually look at asteroids. So here's a really cool one, IDA. One reason that this one is particularly unusual is this one has its own tiny little moon called Dactyl. And both IDA and Dactyl are themselves covered with impact craters. So IDA, by the way, is about the size of Boone County. So anyway. Then sometimes comets. So asteroids are mostly made of rock. Comets are largely made of ice. And the reason we see these great tails on comets is that as they come near the sun, the ice evaporates and we get this streaky tail. Okay, if you get a large asteroid, the largest 4 or 5 asteroids, or any of the planets, they've kind of separated out into layers. We have a metallic inside, the core, and then we have a rocky outside. And so meteorites can either be iron or stony, depending on which of these layers they come from. Iron meteorites, and there's a couple outside you can look at, typically have this kind of crystalline pattern. They are, in fact, crystals of different iron-nickel alloys. And we can actually tell things about how fast they cooled from the size of those crystals. All right, so we know that meteorites are basically rocks. Some rocks are made of metal. How big would the crater be? You guys are doing an awesome job, by the way. So small things, when they fall to Earth, they burn up in the atmosphere. So the fireball at Peekskill, New York, for example, looked really pretty, but just one small piece landed and made a dent in that car. But large ones can survive the heat of friction in the Earth's atmosphere and start to make a decent-sized crater. So one of the most famous is Meteor Crater in Arizona, which is about 3/4 of a mile across. It's about 50,000 years old, and it was formed by an iron meteorite about the size of a football field. So something a little bit, it would have just covered the football pitch in Faroe Field. It probably wouldn't have filled the stadium. And that is called the Canyon Diablo meteorite, and there's a piece of that outside you can look at. So the reason that we have lots of craters in some places, but lots of parts of the Earth we don't see any, is not because they never got hit. It's because, of course, they either got eroded or we can't find them. So this is another picture of Meteor Crater, again, about 50,000 years old, and it's in the desert. And most of the good craters we have are in the desert. Here's one that's twice as big in Namibia, and you can see it's all full of sand. It got eroded around the edge, and it's filled up with sand. Here's one on Mars. Excellent. Thank you very, very much. I think you deserve another round of applause for that job of rolling. All right, so this is a nice, simple crater on Mars. Looks kind of like a meteor crater. It's got a really sharp edge, so we know it must be pretty young. And you can see the debris that got thrown out. This is the kind of thing that I hope you'll be able to make next door in a few minutes. Here's another one. This is Mimas, moon of Saturn. This is the point at which I have to say, that's no moon. And those of you who are, I don't know, my age, I guess, might get that. Anyway, kind of looks a little bit like the Death Star from Star Wars. So that's Herschel Crater. So the interesting thing here is that Mimas is less than 400 kilometers across. It's basically about the size of Missouri. The crater on Herschel Crater there is a substantial fraction of the size of Mimas. And when that impact happened, it must have come very close to completely destroying it. Anyway, we can skip over that. Here's a nice one on Mars. The thing I think is cool about this, if you look at this, what we call the ejector, it's kind of this multi-lobate ejector is what we call it. But if you're a kid looking at this, what do you know that will make that kind of splashy path? Yeah. Sorry. Right, exactly. So wet sand, something wet or something muddy. So this shows us that on Mars there used to be lots of water around, because this is a sploosh. This is not a dry impact. This is a wet, sloppy impact that went over Mars. Anyway, so that's kind of cool. Here's a bigger one. As craters get bigger and bigger, they start to get little mountains in the middle. And there are interesting questions as to what kind of craters are volcanoes and what craters were produced by impacts, but we're not going to talk about that today. Here's a bigger one in Quebec. This one you can see, if you have a look at a map of North America, this one's big enough that it usually shows up on any map of North America. And you can see the ring, and then it's got a central peak again. That's about 200 million years old. This is the biggest one on Earth. This is the Vredefort Dome in South Africa. It's about 2 billion years old and was originally about 200 miles across. When you get to really big ones, this is Callisto, which is a moon of Jupiter. This is a multi-ring basin. The whole moon, the whole planet would have been wobbling back and forth after this impact, and it basically cracked the surface on a whole bunch of concentric circles. Of course, our moon, as I mentioned before, formed by an enormous impact with a small planet called Theia. And this was about 50 million years after the Earth formed, and then the debris from that kind of coalesced and formed into our moon today. At the other end of the spectrum, here is a very, very tiny crater found on a solar panel from the Hubble Space Telescope that is 0.5 millimeter in diameter. So it's like 50 human hairs.
If a big enough meteor hit a planet, could there be a big enough meteor to destroy a planet?
Yes, absolutely. So, could you have an impact big enough to destroy a planet? And yeah, so the question there is, how big is the planet and how big is the impactor? But yes, it is possible. And that kind of happened with the Earth and the Moon. That was back at the beginning of the solar system when the planets were still forming. And the planets formed, actually, by just lots and lots of things colliding with each other. So that doesn't happen anymore, but yeah, certainly used to. Oh, this is NASA doing their experiments. So you guys are going to do something a bit like this, except you won't be using a gun to fire things at a kilometer a second. But we can learn a lot from doing simple experiments. So here we have layers, different colored material on the left, and then you fire a projectile into that. And we notice, if you look real carefully, you see that it got turned over. So when the impact happens, stuff goes, flies up in the air, and then falls over and ends up being upside down. That's exactly what we see around the edge of Meteor Crater in Arizona. Maybe you guys can try do that later. Here's our practice runs from just over 2 years ago. So lots of suspense here while we figure out what's going to happen, and then, there we go. Pretty satisfying, I think. That was kind of an oblique impact. After the initial enthusiasm, we started to do this more rigorously and measure the height we were dropping things from. And this time it's with a ball bearing, which is, of course, very dense and hard. And it's dropping straight down. And we measured it from different heights. And that just made a very small crater. But again, you can see the white rim around there. So that's stuff that's the flour layer that was underneath the cocoa powder that got thrown out. So we still have a flap of ejecta. We got really into this. This is the data, I think, from this evening that we did 2 years ago. Anyway, we have marbles and golf balls, and you can play around and try to figure out what makes different size crater. This is what happens when you let scientists do this for a living, and they come up with something a bit more complicated. But as you're playing around, I want you to think about, try it, drop from one height, drop from another height. Predict before you do it. Is it going to make a bigger crater or a smaller crater? This is kind of how we do science. We play around. All right, last thing. How can we avoid being hit by meteorites? So first of all, we can keep an eye out and pay attention to what's out there. And again, this really only got going after the Schumacher-Levy event, the impact with Jupiter, which was less than 20 years ago. Up to that point, really not many people have been thinking about asteroid impacts. Of course, shortly after that, there was Armageddon, Deep Impact. Hollywood got interested, and then people started to pay attention, and the government started funding it as well. So there are now several programs, and they've been very successful. They've found thousands and thousands of asteroids out there, most of which poses no threat whatsoever, of course. But there are a few. And so here's a nice little animation on the next slide. This is for a period of 1 year. We're going to see it all happen in about 20 seconds. July 2007 to July 2008. So the only objects that are going to be shown are objects that are less than 20 million kilometers from the Earth, which is still quite a long way, right? The average distance to the moon is a bit under 400,000 kilometers. So this is basically objects that are within 50 lunar distances from the Earth. So it's still quite a long way. Objects within a third of this, within about 17 lunar distances, are colored red, and then the next third orange, the other one's green. The Earth will be, you'll see the Earth as 1 pixel moving around. Actually, on the scale that we're showing it, the Earth is smaller than that 1 pixel. All right, let's hope that this works. So this is 1 year. The Earth is the blue spot on the blue line, and all the red things are asteroids that are coming within 17 lunar distance. Oh, lunar distances, obviously, just all going through there very, very fast. And yeah, so you can see that the blue line is changing as we orbit around the sun, and all those red things are asteroids that are coming fairly close as we go all the way around. So that's kind of exciting, I think. You can look up online. If you look up, so Caltech has this great record that they keep of close approaches. So these are all ones that happened last week. Okay, they're not that close. I should emphasize that. So the closest one on there is 2.6 lunar distances, so 2.5 times as far away as the moon. And that was for an object that was smaller than this room, but not much smaller than this room. And it was traveling about 13 kilometers a second relative to the Earth, which is pretty fast. So if you know anything about energy, the speed you're going matters a lot when you're calculating how much energy there would be in an impact. So, you know, that would make a crater if it hit. Normally, the closest approach, if you look for any given week or month, you don't see anything coming very close. This one was for a couple of days after we did this talk 2 years ago. Actually, right on my birthday from 2 years ago. And this one came inside the orbit of the moon. And this one was 400 meters across. The thing that made Meteor Crater was about 100 meters across. So this was quite an exciting one, but that's very unusual. Oh, all the numbers, by the way, the 2013, 2004, this is the year that they were first discovered. You'll notice that most of these things have only been discovered very, very recently, and that's because finally we're actually looking. But it's very important that we keep funding these programs to actually keep an eye out. So obviously that's the preferred solution up there on the right-hand side, if we find an asteroid coming towards us. But basically the solutions, if we were to detect something that was likely to hit us, fall into two options, and you guys get to vote now. So, do you destroy them, or do you try to deflect them? So, basically you can either try to blow it up, or you can try nudge it out of the way. So who's going to vote for blowing it up? Who's going to vote for trying to nudge it out of the way? Okay, and a lot of you are just too terrified to put your hands up. Okay, that's all right. So we know which one Bruce Willis would go for. Well, first of all, let me just mention, I said for asteroids. I hope that we never find a comet coming towards us, because they're typically traveling at about 70 kilometers per second. So not only are they traveling so fast that it would be very, very hard to deflect them, but also they're traveling so fast that we're not going to see them coming until we have very, very little time to do anything about it. So let's hope we don't have any comets. But for asteroids, probably the best solution is deflection rather than destruction, because if you blow up an asteroid, you're not going to blow all the pieces away from the Earth. You're going to turn one impact into lots and lots of smaller impacts. When we do this in class, I explain to the students, what if we had one asteroid and we knew it was going to land in, let's say, Kansas, and it was big enough that it would pretty much destroy Kansas. Well, of course, Kansas doesn't get a whole lot of sympathy. That's maybe not the best choice. But we are next door, so it would, of course, also negatively impact us. Negatively impact being a pun. But anyway, there we go. Accidental. Would you just take one for the team and, have it hit in the Midwest? Or would you blow it up and kind of have smaller impacts in the Midwest, but also accept that you were going to destroy a whole bunch of other places around the world? And so I let people choose. And usually, because they know it's not going to happen, they're very selfless and say, oh, we'll take one for the team. But anyway, it's an interesting exercise to think about. So, the thing about deflection, let me just point this out. The Earth orbits the Sun at a mean velocity of 30 kilometers a second, which means that the Earth moves its own width along its orbit every 7 minutes. So if you can delay the arrival of an asteroid by 7 minutes, you've just saved the world. And if you get 30 years to know that something's coming, you can probably manage to, we could probably figure out a way to delay its arrival by 7 minutes. But there are interesting ways of doing that. Anyway, I've talked quite enough, so I've answered what I think would be the 4 questions that would first spring to mind. I'll be very happy to answer any others. Feel free to go make your own impact crater. Thank you very much.